p87 is asking for the 8th degree Maclaurin polynomial for cosine of 0. All right, so we got to kind of get down to business here. We know f of x is given as cosine of x, f prime of x, negative sine of x. But as I do this, what I'm going to do is find or evaluate this function and its derivatives as we go. The idea being to see if we can recognize a pattern. Cosine of 0 is 1. Sine of 0 is 0 regardless of whether it's positive or negative. Cosine of 0 is 1. Negated is negative 1. Triple prime. It's going to be sine of x. Derivative is 0. The derivative of sine is cosine, so that's going to bring us right back to the beginning of the cycle. All right, so if I need to go to the 4th, 5th, 6th, 7th, 8th, all of 0. I'm just going to repeat the cycle in mod 4. So 1, 0, negative 1, 0, and then back to a 1. All right. So that gets us where we need to go in terms of the coefficients. So now when it comes to writing the polynomial itself, I'm going to say p sub 8 of x. So 1 plus 1 over 1 factorial. It's Maclaurin, so x minus 0, so x to the first. Apologies, that's 0 over 1 factorial. Plus negative 1 over 2 factorial x squared plus 1 over 3 factorial x. I'm sorry, I did it again. 0 over 3 factorial x cubed plus, now we're up to the 4th, 1 over 4 factorial x to the 4th, and I'll say and so on for at least for this moment. All right, because if we simplify this a smidge, we can see that a pattern emerges, and that's going to save us some time. All right, so we're looking at 1 minus 1 over 2 factorial x squared. Ignore the powers of that, well, the power of 3, but ignore the powers that are odd. So plus 1 over 4 factorial x to the 4th. But you'll notice that there's an alternating sign situation. All right, so 1 minus 1 over 2 factorial x squared, the 1 has an x to the 0th, so that's an even power. X squared, even power, x to the 4th, even power. The next one, logically, would be x to the 6th, but since we started with positive, went negative, then back to positive, next one would be negative 1 over 6 factorial x to the 6th, back to positive 1 over 8 factorial x to the 8th. So without having to show all the odd values, we made our lives a lot easier. All right. Now for part B, it says use your calculator to approximate the value of the integral over the interval of 0 to 1, so that the error in your approximation is less than 1 over 500. All right, so that's a little on the strange side, but we'll kind of play along here. It's an alternating series. So when you get into the alternating series, we want to make sure that we recommend. Oh, geez, I'm just making up words now. We remember rules that we've covered in the past. So we have alternating series remainders. all right, which tells us that we only need to go out a certain number of terms of a series if the next term in the series meets the requirement of being less than whatever it is that we want it to be less than, then we're in good shape. But first, I wanted to bring us back to page 79, which was gives a quick refresher on the alternating series remainder. And that's just the idea that if we have a certain number of terms of a partial sum, whatever the n plus 1 term is the remainder, or is the most that the remainder in the partial sum could ever be. All right, so we have that to kind of rely upon. In fact, this is a pretty decent example right here, where we would say, if I want the difference between the actual sum and the approximated form, we want that difference to be less than 1 in 1,000. What I would do is just keep track of the decimal value of each term of the partial sum and compare that to the original given value, which in this case is 1 over 1,000 in decimal form, and see which one's bigger. All right? And then once I get to a point where I've achieved my goal, then I would stop accounting for particular values. Okay, so what we're going to do for this problem is we're going to start off with the recognition that we can approximate the cosine function around 0, because Maclaurin is around 0, using this polynomial function. But I want to just get a quick look. I'm going to start off with cosine. I want to get a quick look of just how far out I can go. All right, so 1 minus 0.5 x squared, every little bit helps, plus 1 over, let me actually delete that, alpha y equals numerator over denominator, 1/4 x to the 4th, minus alpha numerator over denominator, 1 over 6 x to the 6th, plus alpha y equals 1 over 8 x to the 8th. Oops. X to the 8th. All right, making sure I typed it in correctly. Looks good. I'm going to hit graph. Now, over 0 to 1, it looks like the red one deviates some from the black one. The black one is the cosine function. The red one is the polynomial function. We would probably need a few more terms to get where we need to go, maybe even just one more term of the polynomial. So we'll keep that in mind. However, what I want to actually have in the back of my head here is the idea that the red is going to capture more area than the black. All right. So in essence, when we're talking about an integral, we're talking about capturing area. Also, we don't know how the 1 and the denominator of the t squared is going to impact things. All right. So that's part of it, but we'll cross that bridge also. But we do want to keep in mind that we're going to get something that's going to capture more area, not less, so maybe that's acceptable. All right, so we'll see. All right, so we'll start off with, first, let f of t be equal to cosine of t. Let p sub 8 of t be equal to f of t for values of t near 0. All right, so we can make a substitution. So I'm making a variable substitution, t instead of x. That's okay. All right, so 0 to 1, 1 minus, I'm going to use p sub 8 of t over t squared dt. All right, so then I'll pop in my values, or my terms of p sub 8 of quote-unquote t. So I'm going to have the 1 minus 1 minus 1/2, almost wrote an x, t squared, plus 1 over, I'm going to leave it as 4 factorial. And in fact, I'll leave this as 2 factorial for consistency. T to the 4th minus 1 over 6 factorial, t to the 6th plus 1 over 8 factorial, t to the 8th, all over t to the 2nd dt as an integral. All right, so we're going to negate all the terms on the inside by distributing that negative through. So everything's going to get reversed. I'll circle the new sign so I don't confuse myself. All right, 1 minus 1 goes to 0, so that's gone. All right, every term is a multiple of t squared. So I could use that to trim things down a little bit. Speaking of trimming things down, we'd be looking at 1/2, or 1 over 2 factorial, really. I'm going to leave it like that, like I said before, minus 1 over 4 factorial, now it's t squared, plus 1 over 6 factorial, t to the 4th, plus, I'm sorry, minus 1 over 8 factorial, t to the 6th dt, all before we even integrate anything. All right. The process of integration is going to introduce a new variable t for each one, so we're looking at increase the exponent by 1, you know the deal. So 1 over 2 factorial t minus, well, the next one is going to go to a power of 3, so 1 over 3 times 4 factorial t to the 3rd plus 1 over 5 times 6 factorial. Looking at the wrong thing, t to the 5th minus 1 over 7 times 8 factorial t to the 7th over the interval of 0 to 1. Plugging in a 1 really just zaps away all the t's. Plugging in a 0 zaps away all the terms. All right, so 1 over 2 factorial minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial minus 1 over 7 times 8 factorial. All right. So now it's the question, okay, well, what do we do with this? Well, we have an alternating series. All right. The idea here is that there is a progression, and that progression could have continued. We just opted to go with an 8th degree Maclaurin polynomial. But this could go on and on and on and on and on. And in fact, if I want it to be really accurate, I would want it to go on and on and on and on and on. Or at least as far as it would take in order to get us where we need to go. All right. So what I'm going to do is I'm going to analyze this using the alternate series remainder approach, and just before I get into rewriting anything in terms of a summation, I'm just going to see if I have what I need right here. All right. So 1/2 we know is definitely not less than, well, maybe you don't. You type it in. All right, this is our benchmark, 1 over 500. All right, so whatever our decimal is, we want it to be less than 0.002. So 1/2 is 0.5, it's not less than 0.002. All right. 1 divided by 3 times 4 factorial. So 4 factorial is 24. 24 times 3 is 72. So 1 divided by 72. Not small enough, but it's getting closer. 6 factorial is 720. 720 times 5. So 1 divided by 720 times 5 is definitely small enough. All right. So we're where we need to go once we get to this term. All right. This would be the error in our approximation. So that's our cutoff. So it's really the first 2 terms added together that's going to give us what we need. All right. So 1/2 alpha n over d 1 over 2 minus alpha y equals n over d 1 for 3 times 4 factorial math probability option 4 for the factorial symbol, and we're talking about approximately 0.468. All right. So this is what we need. Oop, hit the eraser. I meant the marker. This will get us our approximation. All right. So approximately 0.486. And this is the alternating series remainder. It's not really a test, it's more like a method or approach. All right. So use your calculator to find the actual value. All right. We'll do math option 9. It is alpha n over d 1 minus, I'll use cosine of x over x squared dx, going from 0 to 1, and we're looking at about 0.486. All right. So I did not keep track of the decimal, so let's actually go for that. So this is approximately 0.486. Let's see what the remainder would be. So I'm going to take that answer and subtract from it what we just computed. And it's a little different how you type it in on this one than how you type it in on a TI-84. So I'm just going to kind of do it in a more tedious way, but it is what it is, as they say. I happen to remember this from when we figured it out before, so we're good. All right. So the difference is so the remainder, or the error, is approximately 0.000274. You compare that to 1 over 500, we know it's definitely different. All right, so a very small amount of deviation, which is good. All right, so it's not too far off, regardless of what my graph may appear like. If you zoom out, let me close this and go to a negative. I'll just go a quick negative 10 to 10. On your calculators, you'd hit zoom 6, zoom standard. It's just they kind of ditch that idea because you don't really need much with zooms, because it's a pinch zoom on this calculator. I don't know why it's not working. Okay, because I typed in negative 10 to negative 10. Yeesh, I fixed one of them, but not the other. Negative 10 to 10. Negative 10 to 10. All right, so from this view, it doesn't look like there's much of a deviation at all over the interval of 0 to 1. All right, so it's not really, you get to figure where it starts pulling away is around 1. So that little smidge of deviation is amounting to an area of 0.000274. So not too bad. All right.